Good morning, everyone. Good afternoon, good evening from wherever you're watching this. This is Dipam Paul, and with me is my co-presenter Alankrita Tewari. We are delighted to be here at PyData Global, and we are going to present on the topic today. Anyone can do this, solving the minority class imbalance problem once and for all. So, without much further ado, let's dive in. These are like some of the items that we'll touch upon throughout our talk. And this is just to like set the expectations. We will go in a very step-by-step approach with the entire discussion. So even if you have little to no experience, I don't think you should have a problem. But of course, having a little helps. But yeah, these are some of the things that we'll go over today. So before we begin, this is like a small introduction. Uh, this is me, Deepam. I am from Calcutta. I have, as it's written, I am always passionately curious about, knowing about different things, building things, exploring things. And yeah, that's just me on a nice beach. Over to my co-author.
Hello, everybody. It's great to be here. So, my name is Alankrita, and I am from India. And apart from the things that you can already make out about me from what's given in front of you, the other thing to know about me is that I like to learn about new stuff, especially related to deep learning, machine learning, and this is something that I have been doing for quite some time now. And this like I was also a part of PyData Global last year as well, that is 2020, and have had the opportunity to, be a part of various conferences, all around the world where I get to meet new people and learn new stuff. So that's something that I really look forward to. Now, moving on, what exactly are we doing here, and what is the problem here that we are trying to mitigate? So before we dive deep into that, I would want to touch upon what do we mean by class when we talk about deep learning. So I'll probably take an example that every one of us must have heard of, at some point in their lives while figuring out deep learning. And that is the famous cat and dogs classification problem. So now, in that case, the images of all these dogs from different species and like different breeds, when they're all clubbed together, so that forms a single class. And similarly for the cats as well. So all these different, different colored cats and with different eye colors and different features, and they all of them are like clubbed together under a different class, that is cats. So when do we actually face the class imbalance that we are focusing or emphasizing on about? So this happens when these two classes, in my example, or a multiple, or in the case of a multi-class setup, when there's a class that has relatively very low amounts of data as compared to the other class or classes. So that is when we face the class imbalance problem. And why is it such a huge issue? That is because machine learning or deep learning is a kind of a technology, or is a thing where the model learns from the data that you feed it or the data that it is trained on. So now, if in our example, let's say we have one cat image for every 20 dog images. So and it's been trained on that for like multiple cycles, multiple epochs. And when we try to test that model with, let's say, an unseen image, something that the model has not been trained on, so there's a very high probability of the model or of the, our model giving back a wrong result. So misclassifying or misidentifying an image because of, the inadequate data that it had to train upon. So that is why this problem is something that just brings down the efficiency or the quality of a lot of different models, and is something that we face. And what could be the reason of this class imbalance? There are or there could possibly be n number of reasons when it comes to this. So the ones that are the most obvious or the ones that are the most common that I would want to touch upon is the fact of gold standard of labeling. So now this happens when annotators manually, label data. So they're not 100% right, all the time. And that in case can sort of, cause uh, the class imbalance. And this has to do with human error. And this is something that is there, has always been there. Now, moving on, the one other very common reason could be the fact that we do not have, adequate data for a specific kind of class as compared to the other classes that we are sort of, comparing it against. So this is something that commonly happens with, medical image data and medical data. And that is something that, and that is how we sort of, landed on this problem, or like on the first place. So it was back when my co-author and I, we were sort of working on a project where we had to classify good sperm cell images from bad sperm cell images based on their quality scores and morphology. So now the problem that we essentially faced here was for every 8, 9, 10 bad sperm cell images, we only had one good sperm cell image. So when we tried to, build a model around using that data without any kind of interference from our part through data augmentation, using GANs or, any other method. So the model was performing very poorly. And that is when, it hit us that we have to, look into it, because this could open a lot of different avenues for a lot of people like us. So this is the proposed pipeline, which was based on the project that I talked about. So after redistributing the data into the specific classes, we actually went ahead and, prepared data. We used different kinds of image enhancement techniques in order to, enhance our images to make sure that, the features of our images are, well understood by the model, and which in turn helps us get better results and better performance and makes our model more robust. So moving on, this step, the data augmentation step using CDC GAN, was the game changer for us and is something that me and my co-author will, dive into deeper at some later point in the presentation. Now, the last step that we did was, after augmenting our, data, we trained the classifier using, trained the model on the classifier DenseNet 121, and we sort of chose this amongst different classifiers, pre-trained classifiers such as ResNet 50, VGG 16, all of that, based, simply based on the kind of results that we were getting. So for our images or for our data, it was yielding the best results with this specific classifier. So that is why we went ahead with this. That was the specific reason behind, choosing DenseNet 121. And now once we were done with the training, we validated our model using the or employing the threshold technique. Now, this technique is something that is, needed when we talk about class imbalance and, data and models that deal with class imbalance. So here, what we do is we sort of, put a threshold, as the name suggests, on the parameters that we're dealing with, so that, we get the values within a specific range, which is something that's important. And the why of it, I'm sure my co-presenter will cover in a short. And moving on, we sort of dealt with the evaluation of the said model, where we had to check the quality scores or to make sure the performance was up to date. And the quality scores here were nothing but the number of good sperm cell images upon the combined total. That is the number of bad sperm cell images and the good sperm cell images. So yeah, that is what we did.
Yeah, thank you for that. So now, like, I think moving on to the most crucial part of the entire, presentation, which is basically what the presentation is about. So this is the solution that we are essentially proposing. It's conditional, deeply convoluted generative adversarial networks, or CDC-GAN. So to introduce our audience to this particular network, we have a generator network and a discriminator network here, as is prevalent in your any ordinary GAN. But the difference is that we use multiple, generators and multiple discriminators, which is why it's deeply convoluted. Uh, the function of the loss function is also different here than your ordinary GANs. When we try to optimize a normal GAN with any loss function, it's a little different here. And the most important part is, I think, the first C, which is the conditional, which actually allows us to um, targetedly generate images of a particular class, which is essentially the problem statement here, and which is obviously a very, very difficult task with your ordinary GANs or any other variations of GANs, because you have random images generated, in those cases of the entire dataset. Okay. So now moving on with that in mind, we have this particular idea. So why did we essentially choose this to be the focal point of our entire project or presentation and not something else? Because as I already mentioned, this targeted class, or in some cases classes image generation, which actually is cakewalk with this particular network. It's basically designed for that, one could say. Secondly, consistent performance. Of course, like we tried different other, artificially image generating algorithms, such as, other variations of GANs itself, the simple GAN architecture. We have also used something of the semi-supervised sort of learning, which is variational autoencoders. So even then, of course, CDC GAN in this particular problem statement, and the idea is to put this problem statement into account and treat this as something which is a part of a much bigger problem, which is the minority class imbalance problem that is seen everywhere. So CDC GAN performed extremely well here as well. So now thirdly, we also performed cross validation with like the other architectures that we used, and even there, our chosen architecture, which is the conditional deeply convoluted GAN, performs the most superior. So that's possibly, that summed up the reasons why we were certain that we would go ahead with this and not something else. So yeah, moving on, I think my co-author also mentioned about this in the pipeline, that when she was presenting. So this is a technique, I think, which is already a little known in types of problems like this. So we have a technique called threshold tuning, wherein we generally use this technique in class imbalance problems, or like when we are dealing with data sets which like has a huge amount of class imbalance or a moderate amount of class imbalance, depending upon that. So it's a technique to basically like set different ranges for different parameters, and not allow them to cross a certain threshold that we as a programmer or a deep learning engineer would set. The idea is that your normal perception of how training works or how metrics work is fine, as long as you are dealing with a data set which is perfectly balanced or more or less balanced. But if it's not, then your sort of idea changes, and there are some differences, there are some changes that you have to make in your pipeline as well. And therefore this particular technique comes in really useful, because this not just allows us to set a range within which the parameters would function, but also helps us to not let the class with or classes with more number of examples outperform the one that actually has less number of examples, because that's not a very desirable scenario. um, Lastly, one more important point I would ask my audience to take a note of is that when we talk about unbalanced data sets or imbalanced data sets, accuracy is often treated as a very misleading metric, which is because you have an accuracy for an entire data set. So if a particular class doesn't have enough examples, as my co-author also pointed out, you generally don't seem to get a very, very decent picture of how your model performed on the dataset if you just consider accuracy. So in this particular type of problems, geometric mean and F1 scores are sort of metrics that are preferred, in fact, over accuracy. So yeah, that's basically it. So we are trying to reduce the bias from the entire metrics that we use. So that's the result of the employment of this particular technique and choosing of the metrics, which I think my co-author will sort of go into. Yep.
Now, talking about the validity of the proposed method, as you can see in front of you, we have two different graphs. The first one being the ROC curve, where the area that we get for it is approximately 0.92, which again is in lines of something that we sort of wanted and from our model to work, towards. And similarly for the precision recall curve, you can see the area was nearing 0.89, which again is a pretty good score. Now, moving on, what we did was we sort of trained our models twice. Once with the deployment of GAN, and the second time without it. As you can see, we therefore cross-validated it for like both the cases. So what we noticed was that be it the train accuracy or the validation accuracy, both were considerably high and better in the in the case where we did deploy the CDC GAN, which in turn strengthens our our pipeline or our proposed methodology in this specific case. And as my co-presenter also stressed upon accuracy not being a very reliable metrics in a case of minority class imbalance. So we went ahead and took into consideration some other metrics as well, be it the F1 score, the ROC AUC score, best threshold, or the test accuracy. For all of these metrics, the model or the time where we did deploy CDC GAN outperformed the other time with a great margin. So that in turn did sort of solidify our idea or our intention behind going ahead and using the CDC GAN.
Yeah, I think like that's very important to note, because like the margin that we see here, especially in test accuracy, even if you consider accuracy to be a metric, it's huge, right? If you do not have the artificial examples generated for the minority class, the difference is, so if you do not have it, it's not even something that you would use, because 24% accuracy is uh accurate, inaccurate most of the times. So that's not very desirable. So yeah, finally, I think moving on, at last, we have CDC GAN as a technique, especially it's useful when you are talking about a real world approach to train an architecture, when you have a data which is imbalanced, which is often most data sets, if you think about it, if they're collected on a practical basis and not already artificially generated. And yeah, it's a very useful technique if you want to generate high quality annotated images. And yeah, use the same architecture, fit a classifier at the end, like we did with DenseNet 1-to-1, and have the high quality annotated images come out of the architecture and finally train them. We have higher F1 scores than any other architectures that we possibly could experiment it with, especially in this case, which was a very heavy amount of imbalance. And lastly, there are a lot of randomness that a generative adversarial network brings when you're actually training with it. But surprisingly enough, CDC GAN did not have that, and we could, targetedly generated a lot of high quality images, which were directly useful in the feature selection process in the training of the classifier. So yeah, it's overall, I think, the winner of all the approaches that we sort of experimented with, and that's obviously the reason why you are listening to this presentation. Yeah. So yeah, thank you. I guess that's probably it from our end, and you can obviously reach out to us at any of these email IDs if you have any questions, any concerns, or any further extensions to what we did. And yeah, thank you, PyData Global, and I hope to of course, see you next year. And over to my co-presenter.
Yeah. So I would like to take this opportunity to thank the organizers and all the hardworking people who are the backbone of events like these, which bring together, so many like-minded people from all across the world. And having said that, I would definitely want to encourage each and every one of you to like hit us up with any doubts, questions that you have, or even for a simple fun chat. So I guess that would be fun. Thank you so much.